Hi guys, I'm Aryan Agarwala. Right now I'm 6 stars on CodeChef and Master on Codeforces. Welcome to our channel Learn Competitive Program with CodeChef. If you want to master algorithms and data structures, then this is the one-stop destination for you. Every week we upload problem tutorials on various programming paradigms, and even conduct live problem-solving sessions. So here's a reminder to hit the subscribe button and click on the bell icon to stay notified. Today, we're going to discuss a problem named circle eating, which appeared in the November Lunchtime. This is a hard problem, and the prerequisites are binary search and range query data structures. Specifically, I'm going to use a sparse table in this problem, but you can also use min-max segment trees. It's your choice. Okay? The sparse table is an easier approach though, so if you don't know it already, then I recommend that you check it out. So let's look at the problem statement, shall we? The problem states there are n candies numbered from 1 through n on a circular table. For each valid I, candies I and I plus 1 are adjacent. Candies 1 and n are also adjacent. You want to eat all these candies. So basically, they're like in a loop, right? Like 1 is connected to 2, 2 is connected to 3, all the way till n, and n is connected to 1. Now, your initial happiness level is 0. So happiness level is variable they're introducing. For each valid I, when you choose to eat the ith candy, then the happiness level increases by AI. Note that AI may be negative and your happiness level can also become negative. First, you should eat candy 1. After that, while there is at least one uneaten candy, you may eat any candy that is adjacent to at least one of the candies eaten so far. So first we eat 1, then we can eat either 2 or n plus 1, then or 2 or n, sorry. And if we choose to eat n, then we can eat n plus 1 or 2. If we choose to eat 2, then we can eat n or 3, so on and so forth. And our goal is to maximize the smallest value of our happiness during the process. Okay, so we need to pick a way to do this such that the smallest happiness that occurs during this process is maximum. Okay, now our constraints are, so again, multi-test case format. The number of test cases between 1 and 200,000. N is also between 1 and 200,000, so we're looking at something linear logarithmic maybe. um, AI, which is the happiness value of each candy, is between minus 10 to the power 9 and 10 to the power 9, and the sum of n over all test cases doesn't exceed 2 into 10 power 5. Okay, so let's look at the sample input, right? I've taken this second case here, minus 10, minus 20, 30. So let's look at it here. Okay, so we have three candies, right? Minus 10, which is 1, minus 20, which is 2, and 30, which is 3, right? And they're connected in a loop, as you can see on the screen. Now, the first thing we have to do is eat one. That's not optional, right? That's given uh, by the instruction. So first we eat 1 and we have minus 10, right? Now there are two things we can do. Either we can eat minus 20 and then 30, in which case our happiness level will become minus 10, then minus 20, so it will become minus 30, and then 30, so it becomes 0. So then our answer would be minus 30. However, the optimal way to go forward would be to eat 30 first, so it becomes minus 10 plus 30, which is 20, and then eat minus 20, so it becomes 0. And our answer will be minus 10 here because of the initial candy we ate. Note that if there was no restriction on the first candy, then you could first eat 30, then minus 20, then minus 10, so our answer would be 0. Okay? But since there is a restriction on eating the first candy first, so then our answer is minus 10. Right? So based on this, the circular thing, let's try to make an observation, right? So the first observation we need to make is that this configuration is not really circular. Okay, we eat the first one, then we can keep on going leftward, right? We can eat 7, 6, 5, 4, whatever in a leftward order. Okay, or we can go rightward. We can eat 2, 3, 4, whatever in a rightward order, right? So the left ones are marked by green and the right ones are marked by red. Note that since we have one already eaten, we can delete that element and the list will and this loop will decompose into a linear format, right? Like as you can see below. So all the things that you had to go right to eat, like 2, 3, 4, now those become a prefix of our list, right? And the things you had to go left to eat, 7, 6, 5, whatever, those become a suffix, right? So our problem now becomes that at any point we can eat either an uneaten candy in the prefix or an uneaten candy in the suffix, and we have to find the maximum possible minimum value at any point, right? And we can consider our one separately because that will always be eaten and will always be eaten first, right? So that, like, it's not a variable, so you don't need to take it in part of the problem. Okay. And just to generalize it, we can say that yeah, it's in this way, right? N is connected to 1, 1 is connected to 2. So the prefix is from 2 onwards and the suffix is from n. Okay. So this is a generalized form in which we can change our problem. Okay. So now, considering only the array from 2 to n, we can find the maximum possible value at any state with the initial state 0 included, right? And the reason we include the 0 state here and not earlier is that we only need to count states after which we've already had some candy, right? Earlier, if we included the state right in the beginning, then we had not had any candy then, so that 0 would not make sense. But in this array from 2 to n, the 0 state is after we've had the first candy, right? That's why we count it. Okay? And once we found this maximum possible minimum value in the array from 2 to n, considering only prefixes and suffixes, then we can add a1 to this, right? Because that's non-optional. Now, how do we find this value? We can use an algorithm called binary search, right? So we need a binary search over the answer m. And note that m is only this answer from the array from 2 to n, right? We'll add a1 at the end outside the binary search. Okay? So let's binary search over this answer m. Now we need to check if we can perform the operations as described, which is adding a prefix or adding a suffix from the array 2 to n, and keep the sum greater than equal to m at all times. Okay? Now how do we check this? So first let's define the bounds of our binary search. So the lowest possible value for m we can have is the minimum value of a single element in the array multiplied by the maximum number of elements in the array, right? And that's just minus 10 to the power 9, which is there in the bounds, right? Multiplied by 2 into 10 to the power 5, which is the restriction on n, right? So this gives minus 2 into 10 to the power 14. Okay. And now this is the lower bound, so the upper bound is the maximum value, right? And that will always be 0 because we considered 1 second, sorry, glitch. Sorry for that, guys. Yeah, so this maximum possible value will always be 0, right? It won't be greater than 0 simply because we counted the initial state with 0, right? So how can it go above that if we're taking min? So that's why 0 is the maximum possible value. So our binary search will be from minus 2e14 to 0. So now, first we'll do some casework, right? So first we can check if it's possible to only select prefixes. That is, if you only go right. Okay, so um, if for each valid I, the sum from 2 to I is greater than or equal to m, so that means that we keep on extending our prefix only, then we can keep selecting prefixes and make our solution. So then we're done, right? We say that a binary search is true, so we can go to the success case. Okay, and we can do the same for suffixes. If we can keep on selecting suffixes, then same thing, right? We can check if the suffix is always greater than or equal to m, and so we have a solution. Now, for the general case, if for each I from 2 to n minus 1, let's define si such that si to si plus 1 all the way to n is the longest suffix that we can take if we take the prefix from 2 to I, given that our sum does not fall below m at any point. So that's a really long sentence. Let's just break it down. So we need to find this value si for every I from 2 to n minus 1. Okay? And what is si? Well, let's consider that, again, we're only considering the array from 2 to n. So in this array, let's consider that we've taken a certain prefix, right, from 2 to that value, okay? Now, if we've taken that prefix and we've obviously gone through all the earlier prefixes as well, then what's the longest suffix that we could have taken till this point? Like, what's the longest suffix that we can currently have in our sum, right? So that's what si is. And obviously, it's given that a sum does not fall below m at any point, because otherwise the binary search would be redundant, right? That's what we have to check within a binary search. Now, for any I, if si is equal to I plus 1, then our condition is immediately true, right? Because if our prefix is from 2 to I, and our suffix is from I plus 1 to n, then the entire array is covered, right? So it's true. Now, if for any I, si does not exist, meaning that there's no suffix that we can take along with our prefix, and the prefix sum at I is less than m, meaning that the current sum we have is invalid, we needed some suffix to even it out, then our condition is immediately false, right? And immediately true and immediately false means something here. So whatever happens first between the first two conditions, we can break out then only, right? So if we're iterating through the array and we find an index I where si is equal to I plus 1, then immediately we break and we say that our condition is true, right? We don't wait for the second case to happen where the prefix sum is less than m and there's no suffix, right? And similarly for the second part as well. Like if we encounter this case, then we can't keep on going forward and look for further cases, right? Our condition becomes immediately false, right? And if we go through the entire array and neither of these conditions come true, then our condition is finally false. Okay. Now, how do we actually find SI? As a prerequisite, let's build some kind of min-max range query structure on the suffix sums of the array. Right, so we take the suffix sums in some separate array and we build a min-max structure on that. So we can do this using segment trees if you want, and all of our implementations can be same type complexity, but the only issue that becomes quite complicated. So instead of segment tree, I prefer sparse table. Okay, it's a little more complicated to build, but its implementation becomes much easier in the actual binary search. Okay, so now how do we actually find si? Consider si minus 1, right, which is basically the previous si. Now, if AI is positive, meaning that we've expanded our prefix sum, so now if the value we just added is positive, then obviously the sum will increase, right? And if the sum will increase, then it means that we'll be able to add more elements in the suffix, right? Because we can add like more negative elements to our suffix, and our prefix, which has just gotten bigger, can now handle that. Okay. So in this case, si will be less than equal to si minus 1, right? Like the suffix will shift a little bit to the left, right? Or not shift, really increase a little bit to the left, expand. Okay. Otherwise, if AI is negative, then it means that our prefix sum has decreased, right? It's gone down. So our suffix sum needs to increase, right? So what we'll do is we'll remove some negative part from the suffix sum, right? So like if the last one or two elements were like really small and they were bringing down the sum, then we'll remove them, and so our suffix sum area will contract. Now, some of you might think that why can't we expand it into like more positive elements, right? The reason being that note that the prefix sum earlier was bigger than our current prefix sum, right? So if it was possible to expand it further, then si minus 1 would just be larger, right? Otherwise, like it won't be the maximum possible length of the suffix, so the very definition of si minus 1 will be broken, right? So we can't expand it further and expect the sum to increase. So we need to contract it a bit and remove some negative part. Okay. So in the case where AI is negative, in that case, SI will be greater than or equal to SI minus 1. Okay. Now let's look at case 1. If SI is decreasing from SI minus 1, meaning that the suffix area is expanding, then if at any point j, the suffix sum at j plus the prefix sum at I, like the prefix sum of the area we just reached, is less than m, meaning that it's like an invalid state to add both of them, then it's impossible that si is less than or equal to j, which is the bad index, and j is less than or equal to si minus 1. Why? Because what we're trying to do is we reach the index I, okay, we add this positive thing to our prefix sum, and then we try to expand our suffix sum, right? However, we obviously can't expand our suffix sum to the point j, because that point is invalid, right? The sum will go less than m. So if we expand it, we can only expand it a point less than j, right? Not further than j. So therefore, si will just be the minimum index such that the minimal suffix sum between si and si minus 1. So that's where we use our range query structure. So this minimal suffix sum is greater than equal to m minus pi, and pi is the prefix sum until I, okay? And this is so that when we add pi to our prefix sum, then the overall sum is also greater than equal to m, right? So there's no index j where our condition breaks. So we can easily find this index using another nested binary search, obviously because if you fix one side of the min, then it becomes monotonic. And we can use our min sparse table here along with the binary search for order of 1 queries. Okay, now case 2 is when our binary search is increasing from, when our SI is increasing from SI minus 1, right? Now, we obviously need SI minus 1 to go back to a point where the suffix sum is greater than equal to m minus pi, right? So like I said earlier, we need SI minus 1 to go back, meaning that we need the suffix window to contract a bit so we can shave off some negative part and our sum becomes higher again. So to do this, we just need to find the minimal point j such that the maximum suffix sum between Si minus 1 and j is greater than equal to m minus pi, right? And you guys might be thinking that like how does this work, because we can't actually uh, like uneat some candies after we eaten them, right? So you can't contract the suffix. The reason that this works is this is equivalent to us not eating more candies earlier, right? We're not actually eating less candies in the earlier stages where we decided we'll eat more. We're reversing that and saying no, we'll stop here. And the reason that it doesn't affect earlier indices is we're only shaving off some negative part of the suffix, right? So if our earlier prefix sums are so large they could take some negative part, they'll obviously be large enough to take like a bigger positive part, right? So that's why it doesn't affect the earlier indices. And you can formalize all of this, but I'm just trying to explain it to you. So we can find this index again using another nested binary search, and this time instead of using our min sparse table, we'll use the max sparse table, right? Because our condition for the binary search is based on the maximum suffix sum in a range. Okay. Uh, yeah. So this logic is enough for AC. So let's look at our code. Okay. So this is some code I had written. Okay. So over here, I'm just taking in the number of test cases, and inside this while loop, I'm solving the test cases. Okay. So I'm taking input of n, and I'm decreasing n by 1 because instead of processing it constantly from 2 to n like we were doing earlier, it'll just be easier if we can consider the first element separately, like a separate variable x where I've taken here, and we consider our array to be only the points from 2 to n, okay? And just one edge case that you have to look out for here is that if n is equal to 1 initially, so n is equal to 0 after we reduce it, then there'll be no array to input only, right? There'll just be that single element. And in that case, the minimum value will also be that single element only, right? So you can output that and just move on to the next test case. Now, in all other cases, obviously, we create an array A and we input the entire array, okay? From 2 to n, we input it, right? And we keep the regular indices from 0 to n, like minus 1, okay? We don't actually stay from 2 to n. And now we make our suffix sums in this array called ARR, right? So ARR source are suffix sums. Whoa. Okay, I don't know, my keyboard's locked. So ARR stores are suffix sums, okay? Uh, and here we this build function is just building our sparse tables, okay? The min and max, okay? And this query min function gets the min suffix sum in a range. Query max gets us the max suffix sum in a range. And for those guys who aren't familiar with it yet, our sparse tables gives us order of 1 query, okay? So then now that we built our sparse table, we reach our binary search, okay? So the low is again minus 2e14 and our high is 0, okay? And we said, so this is the answer we keep on taking max on, okay? And initially it's set to the lowest value possible, low, okay? Now while low is less than equal to high, standard binary search, we say m is equal to the middle of low and high, and this is defined here, l plus u by 2, okay? Now we say sum is equal to 0 and prev. So basically when we were sorry we were basing our si on si minus 1, right, as you can see, consider si minus 1. So note that we don't actually have to keep an array s or anything. all we need to know is the previous SI, right? So um, that's what this is. Prev stores the previous SI. Okay. So over here, we're just checking if all prefix sums are okay, right? If any prefix sum is less than m, then we need to check further, so we make this false. Otherwise, if this is still true, then we can just go to the success case immediately, right? And success is over here. Okay, so we take answer as the maximum of m and the current answer, and low is equal to m plus 1, so we look if there's something even bigger we can do, right? And similarly, the fail case here, we just look lower. Okay, so that's standard binary search. That's why I'm not explaining too much. So if this is okay, if only prefix sums are selectable, then we go to the success case, right? Otherwise, again, we reset sum. This is a variable we're using quite a bit. And over here, what we're doing is, so one thing I didn't mention on purpose is that, so for the very first thing, for the prefix sum at 0 or 1 or however you want to index it, what is si minus 1? Okay, so si minus 1 we take the prefix sum as 0, and then we just see how far we can take the suffix with that 0 prefix sum, right? That's what si minus 1 the base will be. Okay, the base case of si minus 1. So that's what I'm doing here. So I is equal to n minus 1, which is the last element. I is greater than or equal to 0, and sum plus a is greater than or equal to m. So basically that means that the suffix at I is also valid without any prefix. Okay, that's what this condition is, and I minus minus. So we add this to our suffix sum, and we say previous is equal to I. Okay, because we keep on changing si as our suffixes get valid. Okay, now if previous is equal to 0, that means that we immediately have a success, right? We can take just suffixes. Okay, otherwise we set sum to 0 again, and from now on sum will store our prefix sums. Okay, so we go from 0 to n minus 2 actually. N minus 1 we're not going to, simply because we already checked this case where we can take only prefix sums, and that's what going to n minus 1 would be. Okay, so we go from 0 to n minus 2. Okay, we add ai to the prefix sum obviously, and now we do our first binary search. Okay, so we check if we can go leftwards. Okay, so basically, instead of taking these two cases separately, first we can just check if case 1 is possible, if it's possible to like decrease si minus 1. Okay, and if it's not possible, then we can just run this binary search again to increase si minus 1. And if we keep on taking min, then obviously it won't actually increase, right? So this just saves us from doing some tedious casework. I'm sorry. It saves us from doing some tedious casework, and we can just do the two binary searches, and they won't affect each other, right? So first we check if we can move it leftwards, right? So is our middle element, and we wanted to see if the minimum from m to our previous one, si minus 1, plus our prefix sum is less than m, then that's a fail, right? So we say L is equal to m plus 1, we need to look for a bigger index, right? So we can't expand it, we need to contract, we can't expand it this much, we need to look for a better one. Now, otherwise, we say tr is equal to min tr mm, so basically, tr is like si, it's storing si, okay? So tr is equal to min tr mm, so this much is valid, right? So we'll say tr is at least like smaller than this, and u is equal to mm minus 1, saying we've gotten here. Now let's look for like if you can expand it even more. Okay, and now this is the second binary search, right? We say L is equal to prev and u is equal to n minus 1. So earlier we were doing it from I plus 1 to prev, so like the left half of uh, the array, considering like si minus 1 is the breakpoint, right? So we checked over the left part to see how leftward we could take it over here. Now we check on the right part to see how leftward we can take it on the right part. Okay, so we say L is equal to prev, u is equal to n minus 1, and then we basically run the same thing, but instead of query min, like I mentioned earlier, we run query max this time. Okay, and yeah, this is good. And if you guys are wondering why we use min here and max here, the reason being is that we're increasing our, in the first binary search, we're expanding our suffix, right? So if we reach any point where we can't expand beyond it, then we need to stop there, right? That's why we're doing min. In this case, we're contracting it. So even if we reach some point, we just need to contract it to a point where we're good, right? We can contract it as much as we want. We'll just reach a point where we're good. Okay? So that's why we use max here. In this, if there's a single bad index, then we can't do it. In this case, if there's a single good index, then we can do it. That's the basic logic. So now if sum is less than m and tr is equal to n, that's a basic fail case I mentioned, then we go to fail. If tr is equal to I plus 1, then we have the entire array covered, so we go to success. And this is just setting previous is equal to si. Okay, minimum n minus 1 tr. And this is just because setting it to n, like if we didn't find anything, so tr is equal to n basically means that we didn't find anything, okay? Like there's no valid si. So if we didn't find anything, then setting tr to n brings up a bunch of annoyances here. So an easier thing to do is just set it to n minus 1. Okay, it doesn't really change. So this is just a failed success like I mentioned. And once we're done with the binary search, to our answer we can just add x, which is like a of 1. Okay, and we can output the answer. So let's run our sample on this. Ah, sorry. For my keyboard's locked. So we have 1 minus 10 minus 1, and like it is 1 minus 10 minus 1, right? So looks good. And we can just submit this. This is basically the same, this is like literally the same code only. But yeah, I'm just submitting it. So while we're waiting for that, uh, the time complexity for this will be 48, and we have a 48 here because that's the number of times our outer binary search will run, right? It'll be log 2 into 10 to the power 14, which is 48, multiplied by n, multiplied by log n for the inner binary search, right? And so that'll be something like 1e8, I think. And luckily our constraint, our time limit is quite large, so this should be fine. Okay. Now, do you guys also know that CodeChef conducts courses on Unacademy? These courses range from beginner topics like Intro to Data Structure, C++, Java, all the way to advanced things like segment trees, DP, graph theory, etc. These courses are taken by top educators like ICPC World finalists, IOI medalists, engineers at Google, Facebook, etc. So all you have to do is either download the Unacademy app or register on the website and choose competitive programming as your goal. We also offer a plus feature where you get things like large problem sets on each topic and live teaching assistants in the form of 6-star, 7-star programmers who clear your doubts during and after the sessions. And if you register right now, then you can use my referral code AGU to get a 10% instant discount. So don't miss this opportunity to kickstart your programming career. Okay. Now, yeah, we got an AC. So,